Okay, ready for a proof? We're going to do a proof of the law of cosines, and I'm going to prove this version, the one that starts with c squared. There's two other versions also, but I'm going to focus mainly on this one. Now there's a couple different ways that you could prove the law of cosines. I'm doing the trigonometric approach to it, but there's also an algebraic approach as well. So I'm just going to focus on the trig since that relates to things that we've already learned in this class so far. Now, I'm starting with a drawing here, and so I purposely am starting with a drawing where one of the vertices of the triangle happens to be at the origin at 0, 0. I'm going to put another vertex on the x-axis, so I'm going to call that's going to be a comma 0. And I have these labeled this way. I'm trying to solve for c, that would be lowercase c here, opposite the uppercase letter there. And so in order to do this, I need to get I want to eventually use the distance formula in order to solve this. So I need to find out the coordinates of this point right here. And I want to have the coordinates for b. I already have those. That's a comma 0. I want to find the distance that goes in between a and b, and that distance should end up giving me this as a result. So now let's go ahead and figure out what the coordinates of this one's going to be. Now in order to do that, what I'll do is I'm going to actually drop a dotted line down here and form a right triangle right there. So let me redraw that right triangle. It's going to look like this. I have angle C is going to be there, and this is an x value and a y value that I'm eventually going to find, and that length right there, I'm calling that length is going to be B. So I want to find these coordinates up here, and this right here is angle C. Now technically angle C here is kind of like a reference angle. It would have the same y value as this. Now whatever angle you put in here, it doesn't really matter. This triangle actually could be drawn in the first quadrant. We don't really know which quadrant it's going to be in, but I know that no matter what, when I put that angle inside here, if I use a cosine, for instance, that's going to give me the correct sign of it. So I don't need to be worried about which coordinate that's in and worry about if I have a negative x value or a positive. I'm just going to go ahead and assume that both these are going to be positive right away. And of course, depending on what I get for angle C, that's automatically going to take care of the sign of x and the sign for y there. Okay, so let's use trig definitions in order to relate the value of c and also the b. Now, because I have a right triangle here, I can use right triangle definitions. We talked about those in the previous section that's using SOHCAHTOA. So in this case right here, if I want to come up with a value for x, I want to use a trig function that relates the x and the side b that I have here. So that's an adjacent and a hypotenuse. So I'm going to use cosine there. That's cosine c equals x over b, adjacent over hypotenuse. So if I solve for x here, I get x is equal to b cosine c. So that takes care of the x coordinate. Now I want to find the y coordinate. And the y coordinate, that's opposite of c, so that's going to use a sine. A sine relates these two sides. So sine c equals y over b. And if I solve for that, I get y is equal to b sine c. So now I have these two, the x value and the y value. They're all related to angle C. So actually now you see it doesn't really matter if C goes beyond 90 or not. Cosine of an angle that's more than 90 is going to give you a negative anyway, so that's going to take care of the x. So right here, this is going to be b cosine C and b sine C on that one, and that's going to be my the coordinates for A. It has to do with, again, whatever the angle this is here, whether this is in the first quadrant or second quadrant, doesn't matter. That will be the correct coordinates for that point at A. So now that I have all that, let's now begin the proof now that everything is all set up. What I want to do is I want to find the distance between A and B, and that's going to involve the distance formula. So let's start with the distance formula. That's the square root of x2 minus x1 squared plus y2 minus y1 squared. That's the one that we're going to start with. In order to do this, I need to have the 2 points that I'm going to use, so that way I can label the x1, y1, and x2, y2. Here's the 2 points I'm going to use. I have b cosine c and b sine c. That's my first coordinate. The second point I'm going to use is a comma 0. These are my 2 points that I'm going to start with. So I'm going to label this one. This is x1, y1, and this is x2, y2. I have all that labeled. Now I can take these points from my triangle and put them directly into the distance formula. Now the d is really going to be c right here. That's the distance. So this is lowercase c that I'm starting with here. And then now let's go ahead and put everything into the distance formula. This is x2 minus x1. The way I have it labeled here, that's a minus b cosine c. That'll be squared. And then I have the difference in the y values. That's going to be 0 minus b sine c, and that's going to be squared. Now the order really doesn't make a difference how you're subtracting these, because since you're squaring the difference anyway won't make a difference here. So I could really label these in any order, but I'm just going to go ahead and label them as is here. Now I'm going to keep on going and do some simplifying now. This part, I want to expand that. So I want to do a minus b cosine c times a minus b cosine c. I got to do a FOIL on that one. So when I multiply that, I get a squared. That's going to be minus 2ab cosine c, and then plus b squared cosine squared c. That's what I'll get when I multiply a minus b cosine times a minus b cosine. That's the fully expanded version. Now what do I get if I expand this? Well, when I expand that one, 0 minus that is just negative b sine c, but when I square it, I get plus b squared sine squared c. The negative gets squared and it turns into a positive. What I want to do next is I'm going to look at these two terms in the end. Now these two terms, this is something that I can actually factor. I have a common factor of b squared that I want to pull out of this. So I'm going to do that right now. I have a squared minus 2ab cosine c, and then I'm going to factor out a b squared, and you get cosine squared c plus sine squared c. The reason why you want to factor out the b squared there is because what we notice in here, this is actually an identity that should look familiar. This whole thing here is equal to 1. Sine squared plus cosine squared, that's an identity that we talked about in the previous section. That whole thing is going to turn into a 1. So therefore, then I can just go ahead and write a squared minus 2ab cosine c plus b squared, and it's really going to be b squared times 1. But the 1 you don't even really have to show, but technically that whole thing will be multiplied by 1 because that's the identity. Now the last thing I'm going to do is I want to make this look like the original one. All I have to do is square both sides to get rid of the radical, and I get c squared here. C squared is equal to, okay, I have a squared plus b squared. If I rearrange the terms I have here, b squared times 1 is just itself. And then I have the rest of it, minus 2ab cosine c. And so now I've shown that this is the same as the one we started with. So now I've proven that. I've shown now that this is equal to this. And again, what did I start with? I started with the distance formula, something we've already talked about that you should have seen before. And then also we have our 2 points. We went through the algebra, and finally we arrived at our answer. This is our one version of the law of cosines. Now if you wanted to prove the other 2 versions, all you would have to do is just change your variables on your triangle. For instance, if I wanted to prove the one for starting with a squared, then I would have a lowercase a and I would have angle A there. And I would just have everything all labeled. But the proof would be exactly the same. I would just be finding the distance formula based on a triangle that's labeled differently. That would allow me to get other versions of the law of cosines. But again, for this version, this is basically what you would do. This is the trigonometric proof, but you also could do it algebraically as well.